All right, y'all, welcome to this video where our objective is that we will be able to create linear models to represent nonlinear relationships by solving for the average rate of change. Usually with linear relationships, we're talking about a constant rate of change. This is going to be a little bit different, but let's just hop into it. So we know that linear relationships have a constant rate of change, so that they're going up by the same amount each time. But if I look over here, well, x is going up at a constant rate. Y is not, right? This is going up by 40, then this goes up by 50, and this is going up by 60. And so the ratios here are not the same, right? And if I put this graph, or I put this line on a graph, it would look something more like this than a straight line. And so this is a non-linear relationship. These happen all the time in the real world. In fact, most relationships are non-linear. That doesn't mean that we cannot create linear models to represent them and make predictions, right? And so if I imagine this as a graph and I have this graph right here, what if I had a straight line? Imagine that orange line is straight. What if I had a straight line that represented it? How could I use that linear line to predict? Well, it gives me after 6 months, what if I want to predict, like it asked me to do in part B, how much savings will I have after 10 months? All right. I want to know this. Well, I can make a linear model to represent this, and I can use it to make a prediction. Will it be exactly right? Probably not. But will it be a useful tool? Absolutely. And so we're going to, let me get myself out of the way here, hop in. So this table represents the amount of months that have gone by in Hector's savings account. Create a linear model that can be used to predict his future savings. Define your variables. So I'm going to create a linear model. It's asked me to make a linear equation. So I know I'm going to use y equals mx plus b to represent a linear function, where b represents the beginning or the y-intercept and m represents the rate of change. So I'm going to start with b, the beginning here. And we're not going to have a you-do for this one. There was a typo in my worksheet, so we're going to skip that you-do. So pay extra close attention to this one. I begin at 100. So I'm going to say that we begin right here at 100. So he begins with $100, right? Because at 0 months past, he has $100. That's our beginning. M, we're going to find the average rate of change. I don't have a lot of space to write. I'm going to write down here in the B box, but this work is for still the first question, A. Say M is equal to the change in Y over the change in X. This time I do not have a constant rate of change. And so I'm going to use the last 2 points, all right? How much do I change on the last 2 points? So from 100 to 250, what was the change in Y? It's 150, right? So he started at $100. By the end of the 6 months, he's at 250. So he changed by 150. And how many months went by? 6 months went by. So he gets $150 in 6 months. He gets $150 in 6 months. So if you get $150 in 6 months, or you save $150 in 6 months, how much money are you saving per month on average? Here we don't have a constant rate. We can still find an average rate of change. So I do 150 divided by 6, and that is 25. So on average, he is saving $25 per month. On average, he is saving $25 per month. Does he save $25 every month? No. Is that the average? Yes. So we can plug this into the equation. Into the m goes 25. And now I can also substitute in variables that make more sense with this exact question. In the x column, I have months, so I can fill in a m for x. And in the y column, I have savings, so I'll drop in an s. So I have something that says this. His savings is equal to $25 per month plus the 100 he already started with. So this equation can be used to make future predictions. And that's exactly what it asks us to do here in B. It says, what is Hector's predicted savings after 10 months? Let me clear this out. I'll rewrite the equation. S equals 25 m plus 100. So what is Hector's predicted savings after 10 months? Well, what do I need to do with this 10? I need to plug it into the m of the equation because m represents months, but variables are for unknown values. Now we know how many months. It's been 10 months. What do we predict his savings will be? So I'm going to rewrite this equation as, I'm just going to not have a lot of space, 25 times 10 plus 100. So what did I do? I plugged in 10 to the m. 25 times 10 is 250, plus the 100 he already started with. We predict that in his savings account after 10 months, he will have $350. How did we make that prediction? Well, we have nonlinear data over here. We created a linear model by solving for the average rate of change. And then we input a 10 into our function. And we estimated that after 10 months, he'll have $350. Okay. Again, we're going to skip the UDO. There's a little bit of a typo in there that I don't really want to dive into. And we're going to hop right to example 2. Here we have a graph. And the graph is going to be the same thing, kind of, where we see that this is nonlinear. Hopefully you understand why this is nonlinear. This is not a straight line, right? It's not moving at a constant rate. So we have nonlinear data. And we want to use it to create a linear model that could be used to predict the number of hot dogs sold in the future. It doesn't ask us to make any predictions. So all we need to do on this example is make an equation and we're good to go. And so let's do that. It asks us to make a linear model. So I'm going to use y equals mx plus b. I'm going to start, the beginning here is a little confusing. I'm going to call it 10. All right, we're going to call this as the beginning right here because we don't have data over here. So we're going to say the beginning is 10. Begin with 10 hot dogs sold. All right. And now we're going to plug in somewhere. Sorry, there's a beeping noise that's distracting me. And now we're going to need to find the m. We need to find how much what was the average rate of change, because we can't find a constant rate of change. Sorry, I had to go pause the video and find that beeping. And so we're going to find the average rate of change here. On average, how many hot dogs did they sell per day from here to here? Okay. And so I'm going to find that by doing m is equal to the change in y over the change in x. All right. I want to use my eraser. This is annoying me right now. Okay. So we're right here, right, at 10 hot dogs, and we end at 70 hot dogs. So how much did the y change if we started at 10 and went to 70? Well, the change in y is 60. And how many days did that happen over? We have no numbers down here, and so we're just really going to count, all right? 1 day, 2 days, 3 days, 4 days. So they sold 60 hot dogs over 4 days. What does that mean? On average, how many hot dogs were they selling per day? They were selling 15 hot dogs per day on average. All right. So our average rate of change, not our constant rate of change for this linear model, is going to be 15. 15 hot dogs. On the x-axis, I have days. On the y-axis, I have hot dogs. And so the linear model, right? What equation did I just make? Something that looks like this, a straight line. All right. I made this line to predict what if I want to estimate how many hot dogs are going to have sold on Saturday? Well, now I can use this linear model to make that prediction. Okay. All right. Final UDO. Let me get myself out of the way here. It's not really a good place to be. Right here. Okay. Go ahead and pause, read the UDO, and try it on your own. Take your time, and then I'll go over it. All right. Hopefully you're unpausing and that you've successfully approached this question. I'll go through it kind of quickly since it's the UDO. The graph shows the relationship between the distance of a car traveled and the amount of hours taken to model that. Create a linear model that could be used to predict the distance traveled given the amount of time the amount of hours taken. Okay, so it's asking us to create a linear model, so you should have known we were going to use y equals mx plus b. B is the beginning here. It looks like the car starts at 0 miles. So I can plug in a 0 for B. You don't actually need a plus 0. It doesn't mean anything. Adding 0 doesn't change things, right? So you don't technically need that. We'll just leave it there for now. And now I want to find the average rate of change because this rate of change is not constant, right? And so I'm going to do that by finding m is the change in y over the change in x. So we started at 0, and it looks like we end here around 250. And so the total change in y is 250. And the change in x is, well, we started at 0, and it's been 10 hours. So what does this mean? All right, they traveled 250 miles in 10 hours. They traveled 250 miles in 10 hours. So to figure out their average rate of change, I do 250 divided by 10, and we get 25. This car is going 25 miles per hour. So I can plug that into my equation. On my x-axis, I have hours. And on my y-axis, I have distance or miles, doesn't matter. And so our final model, our model is saying, hey, this car is traveling 25 miles per hour. It hadn't driven anything before this story started, and that outputs their distance. All right. Hopefully this video made sense. If it didn't, you know what to do. Find your teacher.